Let's start. Previously, we introduced line integration and Green's theorem. Now we're going to have a new topic, which is divergence. Divergence, both in 2D and 3D. These two concepts are used to find the flux and that's in electrical engineering and some other stuff in fluid mechanics. Fluid mechanics, you can find it, that's in momentum, mechanical engineering, fluid for momentum, and deriving other stuff and deriving other equations from other courses. Okay. The equation that we're going to use in divergence is the line integration of the vector given dot product the normal vector ds is equal to the double integration of the divergence, not the curl. You can see that it's similar to the Green's theorem, but it's not. It's actually easier. Okay. These two are equal to each other. When can you use one of them? It depends on which vector you have or which one is easier for you to do that, to solve. So let's say that you have, okay, that's for 2D. Okay. Let's say that you have this example. You have to find the divergence of a vector using the line integration equation. You have the vectors equal to x I hat plus y j hat. Okay, in an area that is enclosed in x squared plus y squared less or equal to 1. Simple sketching. Okay, that's 1. Okay. To solve this, I'm going to start with line integration for this question. This one. To solve this, you already have the vector. What you need is the normal vector. Okay, how to find the normal vector? The normal vector is actually found using the unit vector method. This. Okay, you probably know that. But I have another approach that I suggest. You can see by looking, I want to tell you something. What's the normal vector? The normal vector is when you have an area, any area, okay, whatsoever. The normal vector is the vector that's normal to that surface. Okay, you have any surface. Okay, what's the normal vector? It's actually normal on the surface. That's the normal vector. And when you need the normal, just give me a minute just to derive this. Okay, x, y. When the normal has the magnitude of 1. And the normal is, you see normal vector. This means, let's say I have x and y. The normal must be k. Okay, this can be useful in some approaches. Okay, such approaches can actually be used in 3D, not 2D. But okay, you can know this now. Okay, sorry, I got you just elsewhere. But to apply the normal vector for 2D, you must use this. I got confused. You must use this. Okay, as for the vector, xi hat plus yj hat, and the magnitude is x squared plus y squared. Okay. Okay, that's equal to the square root of x squared plus y squared. Looking back to this, it says 1 or less than 1. So this can be simplified to x I hat plus j hat y j hat. Okay, that's the normal vector. And now you need to find the dot product with the given vector. This will give you x I hat plus y j hat dot product x I hat plus y j hat. Correct? Just give me a minute, please. Okay. There's a mistake here. I don't know where is it. Yeah, okay, it's correct. Okay, to solve this now, by dot product, you just need to do the multiplication with the same vector notation. So this will give you x times x for the I hat, but this is a scalar value, so there's no vectors. And y multiplied with y, that's equal to x squared plus y squared. That's also equal again back to here is equal to 1. Okay, so now substitute in the line integration. Okay, line integration 1 ds. Okay, now how to solve this? How to solve this? ds, see, there are many methods to solve this in mathematics. Personally, I suggest a simple approach that needs a tiny bit of memorizing. dA, when we're using polar, dA can stand for, after integration, it's A, and A can stand for pi r square. That's for polar vectors or uh, polar paths, okay? As for ds, the integration becomes s, and s is equal to 2 pi r, which is the circumference of a circle. I want you to remember these two, okay? And also there's dv, that becomes v, and v is 4 over 3 pi r cubed, okay? That's for a sphere. I want you to remember these three. They're easy. We probably know them maybe from school, but it is important to remember this in this chapter. Okay, go back to this. The integration of 1 ds is just s. Okay, and s is equal to 2 pi r. Okay, now since we then know the value of r again, this one, x squared plus y squared, less or equal to r squared. The square root of r squared is equal to r. The square root of 1 is equal to 1. So go back here, 2 pi, 1. That's equal to 2 pi. So the divergence of this, for this question, is equal to 2 pi. Okay? Now we understood how to solve this using line integration. Now let's try solving it using double integration, or the other type of solution. Okay? Now let's go here. Write the double integration, divergence, dA. Okay? Let's start with this first. Partial over partial x, I hat, plus partial over partial y, j hat, dot product. Don't forget this. This is dot product, not cross product. Please do not make a mistake. X I hat plus y j hat. That's equal to Okay, partial of a partial x, x plus partial y of a partial y, that's equal to 1 plus 1, that's equal to 2. Okay, now substitute back. The double integration, actually, since we have a dA here, this can be to a single integration. To have a double integration, you must have dx, dy, or r, dr, d theta. Okay, to have a double integration. Okay, see, it doesn't matter. So as long as you're solving correctly, okay, dA, and the value of the divergence is just 2. That's equal to 2a. Okay, what's the a, which is the area of a circle? The area of a circle is 2 pi r squared. And we already have the value of r again from x squared plus y squared. And then equivalency that we have is equal to 1, less or equal to 1. The 2 pi 1 squared is equal to 2 pi. Okay, you see, this is slightly easier than the first method, but I think that you must know both of them because there are some cases that one of them can be easier than the other. Okay. Now this is a good example on 2D. Let's start with 3D. 3D is the divergence of vector dv. Okay, it's not wise to use line integration, so just basically stick to this. Let's say that you have a vector of 3x I hat plus 2y j hat. Okay, and it's enclosed in a path of x squared plus y squared plus z squared less or equal to 25. This means that you're going to deal with a sphere. With a sphere. Okay. The sphere has a radius of r is the third root of 25. Okay. Now to apply this, basically just find the divergence, the gradient dot product with the given vector, partial of a partial xi hat plus partial of the partial yj hat plus partial of the partial zk hat dot product with 3x I hat plus 2y j hat. Okay, now let's solve this. And k has basically a 0, so it doesn't matter. So partial of a partial x for 3x plus partial of a partial y, 2y, that's equal to 3 plus 2 equals to 5. Okay, now substituted in the integration. Remember, integration of a dv is also an integration for dx, dy, and dz, and also it is an integration for, I guess, I'm not sure, but we don't have this covered in our curriculum, dz, dr, d phi. That's for your information, but just for you to understand how this is just basically a three-dimensional, so it's dv, triple integration here. And there's the other triple integration, r, dr, d theta, d phi. Okay, that's for cylindrical, and that's for spherical. Okay, and that's for Cartesian. Okay, if you want to check other sources or you don't like my methods of solving, you can check these three different integration, but personally I like to stick with this. Okay. Okay. So again, back to the topic. We have the value of the divergence, which is equal to 5. That's equal to 5v. Integrating dv is just v. Okay, what's the volume of a sphere? That's equal to 5, 4 over 3 pi r cubed. Okay, that's equal to 20 over 3 pi r cubed. Okay, and the value of r is given again back here by taking this. Actually, it's not the third root, it's the second root. I don't know why I got second root, which is equal to 5. Okay, so this gives you 20 over 3 pi 5 cubed. That's equal to, I think that you need a calculator for this, or you don't. 5 times 5 is 25. Times 5, 25 times 5 is equal 125. So 20, 125 over 3 over 30, so over 3, yes, over 3 pi. That's equal to, there's a 0 outside, to 125, 250. So to 500 over 3 pi. That's the value of your divergence for a 3D problem. Okay. There are actually several other problems and equations that you can find from Google and YouTube. I can send you several. They're easier than this, but you can say that's the difficult question that you might have or encounter in an exam. But I'll send you also some other examples from YouTube to check. Okay, now let's go to Stokes' theorem. Stokes' theorem. That's also applicable in electrical engineering and mechanical. I don't know about other courses, but I'm talking about the courses that I know about. Stokes' theorem is basically the line integration of the gradient dot product with uh, the derived displacement, I think. I'm not sure what's this. Okay. And it's also the double integration for gradient cross multiplied with the vector dA. Okay. Yes. So let's have an example on this. Just give me a minute, please. Actually, Stubbs theorem is for 3D and 2D. It's the same. It's the same equation. Just rewrite this. Okay. To solve this, let's try to solve a question. Let's say that you're given a vector of y I hat plus z j hat plus x k hat, and in an area enclosed of z squared plus y squared equals to 1. Okay. And the area is given in the following diagram. The area z, y, and there's x. The area here is given in a quarter circle. Okay, and it has this path, which this path gives you by applying the right-hand rule of this path. Sure, to draw this. Okay, applying right-hand rule to this path gives you a vector coming out of the page or the screen towards you. This means that the normal vector is having a magnitude of 1 toward the x-axis. So the normal vector is equal to uh, I hat. Okay, that's the normal vector. Now to apply this, I'm going to solve it using double integration. To be honest, I don't know how to solve using line integration. So just use the double integration. So the double integration of the curl of this, you must find the curl of this. If you don't know, let's solve it here, just in case. I, j, k, partial x, partial y, partial z. And y, z, x, I think, yes, y, z, x. Okay. I is equal to, if you're going to apply this, okay, partial x, 0 minus partial y of y is 1, so negative 1, I hat. As for j, partial x for x, that's 1, partial z, that's 0, so that's 1, j hat, that's negative, there's a negative here. We must not forget this, j hat, and k hat, partial x for z is 0, partial y for y is 1, so we get negative 1 k hat. This gives us that the curl of this path, or of this vector, is equal to negative I hat, negative j hat, and negative k hat. Okay, now I want you to get this here. Negative I hat, negative j hat, negative k hat, dot product with the normal vector I hat dA. Now simplify this. We know by solving dot product that the I goes with the I, J with the J, K with the K, since we don't have J and K. So that's basically multiplying with 0. So this is giving you that the double integration for this is just negative 1 dA. And again, double integration of a dA is just one integration. We'll get negative A. Okay, what's the area of a quarter circle? We know that the circle is having the area of pi r squared. Quarter, just divide by 4. So this gives you pi, and r, the r is given in previously here. Yeah, z equals y squared equals to 1. This is equal to r squared. Take the square root, and you will eventually get r is equal to 1. Okay, so pi 1 squared over r, that's equal to pi over r. And sorry, there's a negative here. Okay, so Stoke's theorem gives that the solution of this problem is negative pi over r. Okay, for our last example, we're going to have this vector. This time I'll write it in a different way for you, to have to visualize all possible encounters in exam. Okay, y square plus z square, x square plus z square, and x square plus y square. Okay, we're used to write this in a form of a vector as a I hat plus b j hat plus c k hat. This one here is a, and this one is b, and this one is c of this. Okay, it's the same. Okay, now to find the curl, it's not a force, it's a normal vector. I j k and partial over partial x, partial over partial y, partial over partial z. And this one here is just copying this here, y squared plus z squared, x squared plus z squared, and x squared plus y squared. So for the I, j, k, and yeah. Okay, let's start with an I. Cross this, get partial over partial y, x squared plus y squared, minus partial the partial z, x squared plus z squared. That's equal to, for this one, for this, we'll get 2y. For this, the negative stays the same, so negative 2z. Okay, that's the I hat. As for the j, okay, cross this, get partial the partial x, multiplied with x squared plus y squared, minus partial over partial z, y squared plus z squared. This gives you negative 2x minus this term now, minus 2z. That's equal, forget the j hat, that's equal to 2z minus 2x j hat. Now as for the k hat, partial over partial x, x squared plus z squared, minus partial over partial y, y squared plus z squared. Okay, this gives you 2x minus 2y k hat. Okay, now just add these together. I'm not going to because I'm too lazy, because I will rewrite it again anyways. Finally, for the double integration, did I write the double integration equation? Okay, this one. For the double integration, sorry, there's something that I forgot. Okay, that's the solution of the vector, changing it to the curl of the vector. We just, I didn't complete the question to start solving it. That's the problem. I'm sorry for that. dA, just a bit tired. Okay, now we solved this. Now to find the normal vector, we must already complete the question first. We're having a path of y equal to plus n minus 1 and x equal to plus n minus 1. This can be drawn in xyz plane. Okay, this one is z, y, x, and y can be having here. Okay, see, it's just a normal plate on 3D space. Okay, where's the normal of this surface? Knowing that the path is walking this way, where's the normal? Applying the right-hand rule, your fingers will go here, your thumb will go up. This means that it's the normal vector is just k hat, okay? Now, double integration, let's rewrite what we got from the curl. Sorry for this confusion. To y minus 2z I hat plus 2z minus 2x j hat. Okay, I know that I'm solving it in a long way, but I believe that this is the best way to show that you know how to solve that. You're not just throwing some numbers. 2x to y dot product with k dA. Now, okay, here's the k hat also. Now we know since this is a k hat and dot product with this, all of this can be cancelled since they're multiplied with 0. Since the normal vector is 0 plus 0 I hat plus 0 j hat plus 1 k hat. Okay, this will give that since these two are cancelled, and so we're just going to work with this. So the double integration or the integration of area is 2x minus 2y dA. Since we are not having a circle here, we cannot use the formulas of area that we know. So this means that we need to change this to a double integration to x minus 2y dx dy. And as for the intervals, we already have the intervals given from either the diagram or given in the question. So -1 to 1, -1 to 1. Both integration have the same interval. So let's say that I want to start with the dx. It doesn't matter in this case. Let's start the dx. -1 to 1, 2x minus 2y dx. That's equal to x squared minus 2yx from -1 to 1. So this will be 1 squared minus 2y. For the second integration, 1 minus 2y minus x. This will change it to, okay. Okay. To solve this now, you need to expand it or just introduce the signs. 2y minus 1 okay, minus 2y. This is equal to, since these will be cancelled, this is equal to -4y. Okay, now for the second integration, dy, integration from -1 to 1, -4y dy, this is equal to -2y squared. Okay, -1 to 1, -2 out. You can keep it in, it's fine. Just find it easier. 1 squared minus -1 squared. That's equal to -2. 1 minus 1 equal to 0. So the Stokes theorem or the Stokes theorem solution for this problem is equal to 0. Okay. You can review this problem using my summary. I think that it has the same problem set that I solved now. And I think that's it. Do you guys have any solution if there's anyone already? Okay, Omar, do you have any question here? Okay, there's no questions. Good luck for people who are watching the recording.